Hi, I'm Nick Moffat with Verisurf software. Today I'll show you how to use the FARO Arm with Verisurf metrology software to align, inspect, build, analyze, and reverse engineer parts and assemblies. For the demo I'll be using a 9-foot 7-axis FARO Edge Arm. The arm has a number of unique capabilities. Patented temperature compensation guarantees accuracy throughout the operating temperature range of the arm. An onboard computer provides diagnostics as well as basic measurement capability. The arm can run on batteries with wireless communication for cable-free measurement. Custom and standard probes can be calibrated using a simple 10-second procedure. The removable 7th axis handle provides rotation control for laser scanners as well as angled probes. Finally, FARO's patented internal counterbalance system provides neutral buoyancy for ease of measurements. These are just a few of the highlights of the FARO Arm. Next, we'll look at the software. Verisurf's metrology software is built on a CAD platform, giving us full CAD design capabilities. CAD is required for reverse engineering, but it's also very helpful when inspecting complex parts. For example, we can analyze the model, we can pull dimensions from the model, we can even manipulate the model. In addition, CAD tools such as colors, levels, and attributes allow us to manage large part assemblies. Verisurf integrates design, inspection, layout, analysis, and reverse engineering all into a single application. Finally, Verisurf is designed for both print and model-based workflows. I'll start by opening a model of our demo part. Verisurf reads all popular CAD files, CATIA, NX, Pro-E, etc., in their native format. This helps avoid limitations of neutral formats such as STEP and IGES, which Verisurf can also read. When we open a native file, Verisurf saves it in the MCX format and leaves the original file intact. All the data, including the model, measurements, reports, and analyses, are stored in a single file to simplify handling and to prevent data loss. I'll choose the MCX format and then open our demo part. The part is in place and the model is loaded. In the next step, we'll align the FARO arm to the part. After we load a model, we typically align the device to the part so that we can get real-time feedback on tolerance condition. We'll use auto-align since it's the easiest way to align to a model. We start by creating alignment targets on the model to control the orientation of the part. I'll choose Create Targets and then place auto-align targets on the top, front, and side of the model. I'll then choose Run Auto Align and measure the targets as they're highlighted. After the final target is measured, Verisurf aligns the device using a best fit and displays a results dialog. We can review the results and modify the fit if necessary, but since the results look good, we'll choose to accept. When we do, Verisurf runs Inspect Build so that we can verify the alignment. The small deviations indicate a good fit between the model and the part, which indicates that the alignment is correct. This final check is a validation of the entire workflow since it shows that we had the right part, the right model, and we didn't make any measurement mistakes. Auto-Align is a very powerful alignment tool, but it's simple enough for beginners to use. Plus, the results are easily verified using Inspect Build. The FARO arm is now aligned to the part. In the next step, we'll check surface profile. In the previous step, we used Inspect Build to verify our device alignment. Inspect Build is a special measuring mode that displays in real time the deviation between a part and the corresponding features in a CAD model. When we're inspecting a part, the deviation reflects the material condition. When we're moving a part into position, the deviation shows how far to move, and the arrow indicates the direction. Since the arm is already aligned to the part, when we inspect profile, we'll assume that the deviations are due to machining errors in the part. I'll start by measuring points in single point mode on the top of the part. Notice how the deviations are represented using an arrow and deviation text. I'll switch to continuous mode so we can collect continuous streams of deviation data. When the measurements are done, I press Escape, and Verisurf creates an analysis object in the data tree. If I highlight the analysis object, we can see the distribution of deviations in the color bar. And if I double-click the analysis object, we can change the way the deviations are displayed. For example, we can add borders to the deviation text. We can change lines to spheres. If we enable Use MBD Tolerance, Verisurf analyzes the data with respect to the MBD or GD&T callouts for each surface. Otherwise, it uses the global profile tolerance. I'll switch back to our original display and choose OK. And then I'll add balloons to annotate the deviations. I'll choose Auto Add Balloons. Save it. So I have the highs and the lows annotated with balloons. Now I'll highlight the analysis object and create a report. I prefer to have the screenshot on top, so I'll change the order. I'll also change the settings so that we can change our logo. Go from the Verisurf logo to the FARO logo. We can output the results in a variety of formats, including PDF, Word, Excel, etc. I prefer PDF, so we'll leave that there. When we create the report, we see the balloons in the screenshot, we see the FARO logo, and we see the details in the body of the report. We've just seen how to use real-time deviation analysis to check surface profile. Next, we'll use it to position our part. When we use build mode to position a part, we assume that the form of the part is correct and the deviations are due to errors in the position of the part. We refer to this use of real-time deviation analysis as build mode because it's often used to build fixtures and assemblies, but we can use it anytime we want to position an object in 3D space. We'd normally start by aligning the device to the frame of reference of the CAD model, and then we'd build parts into position by moving them to their nominal location. Since the arm is already aligned to the basis of the CAD model, we'll simply move the part and build it back into position. I'll start by just giving it a good rotation. I'll select and build to the circles first because that's a quick way of clocking the part. I'll put the probe in the hole and move in the direction of the arrow. Move to the other hole, try to get it in without moving the first one. Okay, that gets me close enough with the circles. Now I'll escape, cancel the circle selection. We'll show the GD&T, and we'll go back into building to surfaces. Now I have Use MBD Tolerance enabled, so we can use the GD&T profile as our tolerance for positioning the surfaces. In other words, as long as the part is positioned within the surface profile tolerance, we'll consider that it's in the right location. bit. Okay, there's always a tendency to want to build to 0, but as long as we build to green, the part is in the correct position. This is much closer than I need to get it because we want it out of alignment for our next step. This is a very simple example of using build mode. Setting a part in 3 dimensions is a lot more complicated, but the procedures are the same. The part is now roughly aligned. In fact, we'll kick it out a little bit more in anticipation of our next step. We used inspect mode to check our part in real time. In the next step, we'll perform a similar analysis, but we'll start by measuring a point cloud. I'll run inspect build to verify the device alignment. We know the part is good because we've already checked it. We know the alignment is out because we left it that way at the end of our build demo. I'll switch to point collection and scan point clouds around the top and sides. We're not getting real-time deviation analysis, we're just collecting raw probe center data. When I'm done measuring, I'll press Escape and go to the Analysis tab. I'll highlight the point clouds and choose the Analyze button. The analysis results are similar to what we saw in Inspect mode, but the deviations are much larger because of our intentional misalignment. I'll hide the analysis, select the clouds, and run Best Fit. Before I do, I'll reanalyze the data for a baseline analysis. When the fit is complete, we see results showing that the part is good, similar to what we saw in Inspect mode. I'll choose OK to accept the alignment. I can toggle between the before and after best fit results to see the improvement. I'll select the Measure tab and run Inspect Build mode. We can see from the deviations that the best fit is also applied to the device alignment. Inspect mode, which we saw earlier, and analysis, which we just performed, are very powerful tools for model-based inspection. In the next step, we'll measure and analyze prismatic features. All of the workflows we've seen so far have been model-based. We've aligned to a model, we've inspected and analyzed to a model, and we've built to a model. Next, we'll discuss print-based inspection and reporting of prismatic features. We'll align to the part frame shown here, but we won't use a model, so I'll open a new file. I'll start by measuring the plane and circles on the top of the part for alignment. Next, I'll run Feature Align. We can see that the origin is located at the center of the large hole, and the x-axis is clocked by the small hole, so our data is aligned correctly. If I place the probe at the center of the large hole, we can see the device is aligned as well. I'll continue by measuring features, starting with the cylinder in the center. Next, I'll measure a slot. I'll place a tooling ball into the top of the part so that we can measure a sphere. I'll switch to continuous mode and scan the inside of the cone. I'll continue by measuring the hole pattern in single point mode. Finally, I'll switch to point mode and measure the plane on the left end using 4 points. I'll switch to continuous mode and scan the plane on the right side. I can fit a plane through the 4 points on the left side. I'll right-click, choose Fit, Plane, and I'll do the same for the point cloud on the right side. Right-click, Fit, Plane. All of the features that we've measured are displayed in the data tree. If I select a feature, I can see its characteristics, such as its position, size, and form. If I select multiple features, such as 2 points, I can see the distance between them. Or if I select 2 planes, I can see the angle and distance between them. We've seen how Verisurf measures prismatic features. Next, we'll see how to analyze and report the results. We briefly saw the report manager when we reported our inspection results. Next, we'll take a closer look as we analyze and report our measured features. For this report, I'll select the circles and the 2 end planes. When I choose the Reports button, the features are displayed in the Report Manager. If I highlight a feature, we see its characteristics shown in the Details pane. We can use these fields to enter the nominal and tolerance values. I'll enter the nominals for Circle 3 so that we can report its position. The toolbars allow us to add CAD features, to construct features, and to add GD&T callouts. I'll use them to construct the plane and the circle through the hole pattern. I'll start by selecting the circles and then choose Construct Plane. With the circle still highlighted, I'll choose Construct Circle to obtain the circle through the hole pattern. Next, I'll create lines from the constructed circle to circles 3 and 4. I can then select the lines and calculate the angle between them and enter the nominal value. I'll calculate the distance from the constructed circle to circle 3 and enter its nominal value. I can select the end planes and calculate their parallelism. And I can select the constructed circle and circle 1 to find their concentricity. For the last construction, I'll report the position of circle 3. We have all the data we need for the report. I only want the final values, so I'll select them before I create a PDF file. This is a very simple example of a prismatic report, but it shows a variety of constructions and the use of GD&T. Earlier, I referred to the measurement, analysis, and reporting of prismatic features as a print-based workflow, but it works equally well, if not better, with a model. Verisurf's reverse engineering tools allow mixed modeling with prismatic features, meshes, and NURB surfaces. In addition, we can take advantage of the many CAD tools inside Verisurf. For the demonstration, we'll scan and then surface the contour on the top of the demo part. I'll start by scanning the top of the part. When I've measured the cloud, I'll select the Reverse tab, highlight the cloud, and choose Patch. The fit parameters allow us to control the complexity and the accuracy of the surface. I'll verify the probe offset and then create the surface. When the results are displayed, we can see the values are in range, so we'll accept the results. We now have a surface that the parameters indicate is good, but how can we check it? On the Measure tab, we can use Inspect mode to compare the surface to the part. We can also analyze the point cloud to the surface. Since the data from the arm is traceable, we have a way of proving the accuracy of our surfaces. This was a very simple example of reverse engineering, but it shows how easy it is to use Verisurf to create and to verify surfaces. That concludes the demonstration. I hope I've given you a good appreciation for how Verisurf metrology software enables the FARO Edge Arm with a complete set of model-based tools for alignment, inspection, tool building, analysis, and reverse engineering. For more information about FARO Edge portable CMMs and Verisurf metrology software, please contact FARO Global Headquarters at 407-333-9911.